One of the most important concepts that you want to understand as a student when it comes to pulleys is no matter what the pulley configuration looks like, no matter what the diagram looks like, you do these questions the same every single time. So your goal, and 2 examples isn't going to be enough. We're going to have to go on and do some work after this. But your goal is to come to a point where no matter what a pulley looks like, you follow exactly the same steps. So let's look at this pulley instead. It's actually the same numbers. It's the exact same masses. I think I labeled them differently though, M1 and M2. So let's see, yeah, let's change these around. Call this M1 and call this M2 just so it matches the masses we used on the previous diagram. So this is 12 kilograms dangling off the desk, and this is 5 kilograms. This time it's not dangling. It's sitting on top of desk and it's going to slide forward when the pulley system is let go. Now when you're looking at the pulley system, you should be able to look at it and understand right away which direction it's going to move. The 12 kilogram mass is not only is it greater, but it also just makes sense. The 5 kilogram mass is not magically going to pull the 12 kilogram mass back up onto the desk. So our positive direction looks like this. I've got a marker that has pretty much completely run out. I hope you can still see that. You know, that is the positive direction. So anything in this direction, we're going to label it as positive, and anything opposing that, we are going to label it as negative. I'm getting a little bit ahead of myself though. The very first thing that you need to do on a pulley question is look at the diagram and label the forces. Let's start with mass number 1 since it's exactly the same as before. It's dangling. There's a force of gravity on this, and that's all. Force of gravity. Number 1. The mass that's up here on the desk. Think about your grade 11 questions when you had objects sitting flat on the ground. Yes, there's a force of gravity on this mass, number 2. There has to be. But there's a desk underneath. The desk is pushing up with a normal force. And that mass doesn't rise into the air or collapse into the desk. So these cancel each other out. They are there, but they cancel each other out, and they're not even part of the pulley system. What will happen though is as this mass number 2 is dragged across the desk, there will be a force of friction opposing motion. So that's new in this pulley calculation, but it's certainly not new in your background of physics. Of course there's a force of friction. You're dragging across a surface. So that's it for this question. However, remember, you have to go back and say that the rope itself has a force of tension in it. You must label that force of tension, or else you're going to get part B of the question wrong. Label the force of tension, label it twice, both ends of the rope. You will draw a force arrow for the force of tension, and you face it back toward the pulley. So force of tension here, force of tension here. So with those 2 forces up top canceling each other out, there's still 4 forces in this question. The solution for part A is going to look virtually the same physically as it did for the last question, but at the same time it's going to be different. It's going to have a different kind of force in it, friction. So what will be the acceleration of the system? We're going to do this. Acceleration is going to be net force divided by mass, but I'm going to write in total mass before I forget. Really, honestly, if you forget to write in that word, you're eventually going to cancel masses, and masses never cancel in these questions. Your second line is probably one of the most important lines because you have to get every force arrow in that diagram into that net force formula, and you have to follow the sign convention. So positive direction here is anything that goes to the left and down. Let's start at the tip top of the arrow here, the tip of the positive direction. We've got a force of gravity on mass number 1. And I'm going to put a positive sign in front of it. Even though the positive sign doesn't mean anything and it's not going to affect the math, putting a positive sign in front of it reminds you that you have to think of the sign on each one of these forces. Next up is a force of tension, and it's in the negative direction. Next up after that is another force of tension, this time in the positive direction. And then finally, at the very end of this list, in the negative direction, a force of friction. These two tension forces cancel, which always happens. And again, you're going to eventually get lazy and say, why even bother writing them? But write them in there anyway. You're dividing by the total mass. The third line, you got to break these formulas down. For those of you in grade 11 that had some trouble writing general formulas on just a regular question, now you're getting into work from now till the end of university where you might have several lines of general formulas. I need a line that's going to show the variables I'm going to sub into. So force of gravity is mg, and I'll specifically say mass number 1g. Cancel, cancel. Negative force of friction. Now this is a mass that is sitting flat on a desk. It's not a ramp like it was yesterday. This is just a regular grade 11 situation where force of friction is coefficient multiplied by normal force. And actually I'm going to be a little bit more specific. I might as well do it right in this line. The normal force is going to be equal to force of gravity. And the formula for force of gravity is mg. So I'm going to write it like this instead. Coefficient multiplied by mg, and that's mass number 2. I hope I didn't go through too many things there and confuse you. On the bottom is still the total mass. Now, don't try and cancel masses because none of them are the same. Let's just put in all these substitutions. So mass number 1 is 12 kilograms. G is 9.8. I'm going to write newtons per kilogram. Got to make life exciting sometimes. That's sarcastic. The coefficient of friction, I forgot all about it, but it must have been given way up in the beginning of the question. Here it is here. 0.2 between the mass and the desk. So 0.2. Mass number 2 on the desk is 5 kilograms. And G again is 9.8 newtons per kilogram. And we're going to divide all that by the total mass, which is 17 kilograms. Okay. So let's see how these numbers are a little bit different. 12 times 9.8 is the same value that it was in the previous example, 117.6 newtons. The force of friction is going to be a completely different number though because of that coefficient in front. This time it is, oh, that was a coincidence, 0.2 times 5 times 9.8 ends up being 9.8. So it's 9.8 newtons, and on the bottom 17 kilograms. Do this math and you can see if you look at the units there that we're going to get an answer in newtons per kilogram, which is another way of saying meters per second squared. 6.34, but don't stop. Just like the last example, the more you write here the better. 6.341176, I think that's good enough, meters per second squared. You want to have a nice, very specific acceleration so that when you do part B, you get the most accurate answer possible. Okay, so that's it for part A. And then for part B, when you have to solve for the force of tension in the rope, go back to your diagram, exactly the same as before. Pick one of the two masses, it doesn't matter which one, and you're going to write a net force formula for just that mass. And this mass over here on the right where these forces canceled out, you can still leave these forces canceled out. You don't have to use them. We're just going to use the forces that were in the pulley formula. So you got two choices. You can write a net force formula for this one, or you can write a net force formula for this one. And I don't think either one of them is easier or harder. I'm going to pick this one just because force of friction is a bit different. I'll use this one here. So let's write a net force formula for just that mass in part B. So we will have this. The net force of just this mass over here, keeping the same sign convention as before. There's a positive force of tension and a negative force of friction. break the left-hand side of this formula down into MA right away. If you don't do that, you're not going to be able to solve it. So break that down into MA. And you got two choices here, I suppose. If you wrote out a lot of information in part A, you already worked out what the force of friction is. I did. I worked it out here and got 9.8. You got two choices here. You can rewrite all the variables and sub in again, or if you're very careful with work you already did, look up there, find it again, be careful, make sure you're finding the exact value, and you can reuse it. So I'm going to write 9.8 newtons because I know from the previous calculation what it was. You want to isolate for force of tension, and you want to substitute in your acceleration from part A. So bringing this to the other side is going to change it into a positive. We're going to have MA plus 9.8 equals the force of tension. And let's do these substitutions. The mass, be careful, don't use 17, don't use 12. This is a net force formula for just this 5 kilogram mass. So it's 5 kilograms. The acceleration is the acceleration from part A, and the less you round it, the more exact the answer is going to be. 6.341176 meters per second squared. Plus 9.8 meters per second squared is going to give me the force of tension in this question. And you may find when you pick up your calculator, since you haven't done really any calculations since, your acceleration answer is still waiting for you, uncleared on your calculator. That's always a bonus. So I'm just going to take that answer and multiply it by 5 and add on the 9.8 for a hopefully perfect answer of 41.5058 This time I'm going to write it pretty confidently as 41.5. 41.5. Now if you repeat this calculation, and you can do it on your own, if you take the other mass and you write a second force of tension formula, or a net force formula for just this mass, and you go through the work, you should also get 41.5. So you got some choices here to realize how to do it correctly. You should never have an answer to a pulley question where you're not quite sure if you did it right or wrong. On a test or a quiz, maybe, because you might not have time to do it twice. But if it's on an assignment where you've got some time to check your work, they're always checkable, which I found very, very valuable in university, because it was nice that you could check and see if you got it right before you just handed it in. All right, what else? So, a couple of little notes that I want to write just to finish this off. If you look back through these two examples, you're going to see that the word ideal popped up a couple of times. In the very first question, the description, if I zoom in here, says two masses are held in an ideal pulley system. And I bold-faced it on purpose. Second example, right at the top, there it is again, the same ideal pulley system. Well, what the heck is an ideal pulley system? Well, if you read the top of this page, it says these calculations are going to get far more complicated in first-year university. But you have to start somewhere. You have to start with the basic skills and be able to work out these questions. So high school pulley questions are a little bit easier than they're going to be in university, and they're considered ideal because of a couple of things. Number one, the M total. The total mass that you use on the bottom of these pulley systems is the mass of the entire system. And in high school, we just, let me throw this one down in front of you here, we just include these as our masses. But technically, the pulley itself has a mass. It could be a very, very light pulley made out of plastic, or it could be a giant cast iron pulley that's very, very heavy. The masses could be exactly the same. The pulley itself could weigh more and therefore be harder to turn because of its own mass. Also, you could argue the rope. The rope definitely matters. If it's a thin little fishing line with masses attached to it, it's going to act differently than if it was a giant, thick rope like the ones that are hanging in the gymnasium at elementary school. You'll get totally different results. So the M total, the pulley and the rope. I'll put rope in italics because it doesn't have to be literally a rope, but the pulley and the rope are massless. And that is physically impossible. There's no such thing. Okay, that's number one. Number two, the pulley itself, like the wheel of the pulley itself, has no friction. That's impossible. There's no such thing as a frictionless object. The pulley rotating has to have some kind of friction of its own, and there's no formula for that. Like, that's a very difficult thing to consider because you can't just write a numerical expression that would describe the variables involved in that friction. It could be rusty. Like, seriously, it could be a metal pulley that has some rust building up on the inside of it, and it doesn't turn as easily as it would normally. So in high school, the pulleys just don't have any friction whatsoever. And I wrote a third bullet, but no, I guess that's it. That's what makes high school questions perfect, is you never have to consider how much the pulley weighs. You never have to consider how much the rope weighs or the mass that it has, and there's no friction inside the pulley itself. What I wrote here in the diagram section is I took every single pulley question that I found on tests and quizzes that I had used before, and I drew diagrams of them all. This looks scary as all heck. Every single diagram here is completely different than what I just showed on this page. And some of the homework questions on today's work look similar to these diagrams. Listen, if you stare at all of these diagrams, not that you're going to sit here and stare at them, but if you stare at these diagrams and get over the fear of what they look like, you do the same thing for every single question. It doesn't matter what the diagram looks like. The first thing you do is put your force arrows on there. And I can see that there's a couple here that are on diagonals. There's ramps involved. Well, that's yesterday's work. So far, none of the examples have ramps. But if you have a ramp, like for example, this question here in the middle, you've got a force of gravity straight down. That's it. And then here you have a mass that is being pulled one way or another. I'm not sure which way it would be pulled actually, whether the 50 is enough to lift the 100. I guess not, that'd be impossible. The 100 pulls the 50 up in the air and down this side of the ramp. So this entire mass is moving this way. Well, when you have masses on a ramp, you always have a force of gravity, but that force of gravity is the ramp version of gravity, mg sine theta. And you always have friction opposing motion. So if the 100 kilogram mass is sliding down the ramp, it's got a force of friction up, coefficient mg cos theta. That looks worse than the question we just did. There's three forces. I didn't label this one, but it's just an mg. There are three forces, and you have to put the force of tension in there on both ends of the rope. So you've got a force of tension facing up toward the pulley and up toward the pulley. Force of tension, force of tension. That looks horrific, but I'm telling you right now, there's only one forward direction to any one of these questions. And every single force that's in the diagram just goes into the net force formula. And what difference if there's 2 forces or 5 forces or 10 forces? All it's going to do is make a longer net force formula line. That's it. A little bit more bed mass and a longer result. The steps are exactly the same. Once you label the forces, all you have to do is put those forces into a net force formula and work out the acceleration. Everything's the same, just maybe more complicated because there's more things to sub in for. But if you look at every one of these diagrams, and this is what I wanted to put at the bottom of the page, no matter what the pulley system is, you're only looking at 4 possibilities. Individual masses, I mean. If you look at the individual masses, there's only 4 possibilities in every one of these diagrams. You've either got a mass dangling straight down, or you have a mass that's sitting on a flat surface, or you have a mass that's on an angle and it's being pulled up, or you have a mass that's on an angle and it's being pulled down. Yes, that is possible. But that's it. Those 4 diagrams are all that you have in every one of these questions. And it's almost like Lego. These are your 4 Lego pieces. And every single one of these little diagrams, you could easily write on all the forces. A freely dangling one just has a force of gravity. One that's on a flat surface being pulled forward only has a force of friction. One that's on a diagonal being pulled up the ramp has mg sine theta always, and it would have a force of friction opposing its motion. Coefficient mg cos theta, and they'd be in the same direction, almost like that hockey puck question yesterday. Or you could have a mass on a ramp where it's going down the ramp, and in that case you would have this. You would always have mg sine theta down the ramp, because mg sine theta, gravity is always affecting masses that are on ramps in the downward direction, and you'd have friction opposing it. Coefficient mg cos theta. That's it. What I mean is, no matter how complicated a diagram looks for a pulley, you actually only have 4 possibilities for putting forces on them. And if you understand each of these 4, that's pretty much it. I suppose maybe I should have wrote this. Instead of writing force of friction, I should have wrote coefficient mg, because it's flat on a surface. And instead of writing force of gravity, I should have wrote mg. So there you go. These are your 4 possibilities for putting force arrows on an individual mass. I didn't put the force of tension on any of these because that's in every question. So, even if you get a pulley question that you have never seen before, like this one, it looks completely different than anything else in example 1 or example number 2. And let's say you are on a test or a midterm exam and you get a pulley that you've never done before. Don't look at it and say, I'm dead. I don't know how to do this. You do know how to do it. Label the force arrows on the diagram, and as long as you get all the force arrows on there, you're just going to put individual grade 11 formulas, except for the 2 ramp formulas, I suppose, from grade 12, but you're going to put easy formulas that you've already seen into a net force expression, and you're going to divide by total mass and get an acceleration, regardless of how new the question looks. So hopefully you wrote these 4 things at the bottom of the page, because literally those are your only possibilities. So we're going to see how this works out by doing a couple of examples or a couple of questions. I wrote on the back, there are 3 questions from the textbook, and there were 2 questions from a previous textbook that I kept in here. Let's save these, okay? Save additional question 1 and additional question 2. First, let's start on these 3 questions. You can do additional question 1 and 2 if you want, but I may change them around a little bit from the way they're worded here right now, because I see that you are you're solving for masses. There's a what do you call it? A rotation of the unknown in these questions, and they're not quite exactly the same as the examples. So yeah, let's start with these 3 questions. Pretend that these questions aren't even on the page right now. We'll do these 3 questions first, and then we'll have like a part 2 to this. And I'll rewrite these questions perhaps so that they're matching the examples a little bit more. There's some tips and tricks at the bottom here, so I guess the first 3 tips and tricks will still apply. These 3 here. You can read those as you're doing the questions. And I'll post full solutions to those 3 questions so that you can go through it line by line. And we'll see where we go from there with a kind of a second half, a part 2 to this. So there's only one topic today, and that's pulleys. In the afternoon session, cohort A is going to be doing their first quiz number 1, and cohort B, I will make a suggested post for you about what you can work on if you want, or you can get ready for your quiz, because that's going to be tomorrow at the end of the day. So that's it for now. Do these questions first, You may run into some little snags because it's the first time going through any of this, but we will, you can go through the full solutions that detail every step, and I'll write out some good paragraph descriptions as opposed to just lines of work.